Good afternoon. Good afternoon. We're really excited to see a full house to hear about a deep dive for AWS's newest fully managed graph database service. Just before we get started, I wanted just to do a show of hands and just to kind of understand the audience a little bit. How many of you know what a graph database is? OK, that's good. How many of you are using or have used the graph database? OK, a few. How many of you know what a property graph is? Good. How many of you are familiar with Rdf, or the Resource Description Framework? OK, great. Hopefully, we'll have most of the hands up in the air for a lot of the questions by the end of it. So, we've had over 700 people request access to the preview since our announcement yesterday in Andy's keynote. And so we'll be, if you are among those who've requested access, we'll be getting to you very soon. But we're really excited about the interest here. So to kind of give you an overview of what we'll talk about today, I want to talk about the challenges of building applications over highly connected data. And you might really think of this as, why did we build Amazon Neptune? What are the problems that we're trying to help our customers solve? And then go into an overview about the different types of graphs. Give you an example about using Apache Tinkerpop, which is an open source framework, for a recommendation engine example. I'll give you an example about using an Rdf knowledge graph. And then I'm going to bring my colleague up, Bruce McGaughey, to talk about some of Neptune's fully managed enterprise-ready features in the platform. So let's go ahead and get right in. So today's applications need to process data that's both rich and highly connected. It's rich in that it comes from heterogeneous sources. Each individual item of information has different units in it. And it's highly connected in that the information relates to other bits of information. And you can build applications that exploit this connectivity. And so you see things like social networks, recommendation engines, fraud. They're all examples of applications that are using highly connected data. There's a breadth of things that do that. Social networking we talked about. Knowledge graphs are a way you can use a graph technique to model information to improve information retrieval. Fraud detection. There's a breadth of use cases in the life sciences, ranging from drug discovery to master data management and data integration. And then networks are inherently graphs. And so there's also a breadth of use cases in terms of managing networks, detecting anomalies on networks. So it's just a very, very rich and exciting space to work in. So let's go through a couple of examples about how you can use the properties of connected data to build these kinds of applications. So the first thing we're going to look at is a very simple recommendation example. Here we're using connected data. And what we're going to look at is cases where there's shared connections, but where the actual fully connected data can be completed. And so if you look here, let's see if we get this working. So you can see that we have 3 people here who follow a sport, and 2 of them have purchased a product. So we can make a recommendation by, this is a technique that they call Triadic Closure, by completing this link to be able to say, this person may also want to do this. We can do the same kinds of things in a friendship context. Same example, except making a friend recommendation. I mentioned knowledge graphs. This is an example of a very simple knowledge graph. It takes a look at some artwork, and it's derived from one of the W3C knowledge graph examples. You can see we have the Mona Lisa, we have the painter, we have the location. And when you model this information in a graph, it helps you answer questions. And you can say things like, who painted the Mona Lisa? What museum should Alice visit when she's in Paris? What other artists have paintings in the Louvre? And by building these kinds of knowledge graphs, you can use them to improve information retrieval. We're very excited that Thomson Reuters is participating in the preview for Neptune, and they've provided this quote for us. They have a very interesting graph use case. They're looking at using a graph to model different tax policies and different regulations, and then helping their customers to be able to navigate that sort of complex web, if you will, of different regulatory information. So how do you build applications over highly connected data? Can I use a relational database for this? Well, you can, but there are some challenges. One of them is that SQL is really not designed to process relationships well. And so if you've ever tried to build a SQL query across a number of different tables, you end up with a lot of nested joins, and the SQL itself becomes quite complicated. It also, as the number of relationships grows, the ability to process it very quickly degrades, and so you have performance limitations. The second aspect is that graph workloads have very different I/O requirements than you get in a relational database. And so relational databases just aren't optimized for processing queries over highly connected data. And then the third challenge is that what we often see is that with highly connected data, the types of information that you want to process are changing very rapidly. And so you want to be able to flexibly accommodate new data types very quickly and then be able to use them within your application to drive new features. And relational databases don't evolve their schemas very well. They're relatively inflexible. So consider an example here. And here we're thinking about an HR example. And so on your right-hand side, you have sort of a relational model of an HR system. And on the left, you have a graph model. And suppose that you had a scenario where one of your top employees unexpectedly resigned. And you wanted to ask the question, what skills do they have? What products do they work on? Who do they know? If all you have is the relational model that's sort of been built for the business application in the HR system, it's really very complicated for you to answer that question. You have to come up with one of these multiple join SQL queries that we talked about earlier. If you've modeled your data as a graph, then you can ask that question much more naturally, much more easily. And this is really sort of the power of looking at graphs as an approach for processing highly connected data. So a graph database, like Amazon Neptune, is a database that's optimized for storing and retrieving highly connected data. It also supports query languages that allow you to easily and concisely express graph traversals and graph patterns. And so a graph database is really a key to building applications over highly connected data. There's two major models for processing graphs. The first is something called a property graph. A property graph consists of nodes and node properties and edges and edge properties. The most popular open source framework for property graphs is something that's called Apache Tinkerpot. And it provides an imperative traversal language, which is called Gremlin, to allow you to write traversals over your graph. The second graph model is something called the Resource Description Framework. The Resource Description Framework, or RDF, is based on a set of standards from the World Wide Web Consortium that's collectively known as the Semantic Web. RDF defines a resource-based model for describing graphs. And so in RDF, and we'll have a more detailed example later, there's resources, which consist of uniquely identified URIs or IRIs. And then you can associate attributes with those resources, and you can make relationships between those resources. And that's how you build up the overall graph model. Now, when we looked across the alternatives that customers have today for processing graph databases, a couple things stood out to us. We heard repeatedly from customers that they had challenges with their applications. They often would do a proof of concept or a prototype, and they'd get very good results. But when they moved to the next stage, they weren't able to maintain the query throughput and the query latencies that they experienced at a smaller data scale. And so they had declining performance at increasing data scale. Another thing that we heard was that it was very difficult to configure features that you need for an enterprise production application. Things like high availability, read replication, encryption at rest. In fact, we met with a customer this morning that was using a graph database. They were working on configuring it on EC2. They weren't able to get the high availability clustering working. They had the vendor come in. They were also not able to get it working. It's just very challenging to do that. So the third area we found out was that things are very expensive. Often you get started with an open source solution, and as we talked about earlier, you'd have a successful prototype, and you'd want to move it into production. But when you had to do that, you had to license the enterprise edition, and that was just something that was cost prohibitive. And then the last thing that really stood out to us was the lack of choice. And many of the existing alternatives tend to track you towards one graph model or another. While they may support Tinkerpop or Property Graph and RDF, they tend to have a strong bias in terms of performance towards one model or the other. So with that in mind, we developed Amazon Neptune. So Amazon Neptune is designed to be fast. In particular, it's designed to be fast for graph applications that require high throughput and low latency graph query answering. Amazon Neptune is designed to be reliable. The gaps that we saw in alternatives, we tried to address with Amazon Neptune. So we support multi-AZ high availability. We support up to 15 different read replicas. We support encryption at rest with customer-managed keys, all in a fully managed experience, which makes it easy for you to build graph applications that use either Gremlin or Sparkle, depending on what you think is the right fit for your application. So this is a look at the high-level architecture for Amazon Neptune. You can see across the top, we have sort of the data plane or the data APIs that you'd use to build applications with. Amazon Neptune itself is a purpose-built engine that's designed and optimized for processing graphs. It's both durable and ACID and provides immediate consistency. We also are running on top of a cloud-native storage layer. This allows us to offer the enterprise capabilities and the fully managed experience that we talked about earlier. The other kinds of APIs that you have from Neptune, it's great to be able to query the graph and to be able to build applications, but you also need to get data in and out. And so we're able to provide a bulk load API for you to load data quickly that you have stored in S3 into the service, as well as to perform database management type operations. So let's take a little bit of a look at the different types of graphs and how you build applications against them. We talked about a property graph. This is a little bit more of a detailed example of what a property graph is. So we have the vertices here. In this case, this vertex has something that's called a label. A label is used in property graph very similar to a type. And then we can see that we have an attribute here, which is a name. It's called Bill. And between these two vertices, there's an edge. And this is in this case, the edge has a label, which is like a type, that it's a friend. And we're making that relationship to another vertex instance, in this case, Sarah. And each edge and vertex has a unique identifier in systems. And the properties express the different attributes on both the edges and the vertices. Now, as we mentioned before, Tinkerpop is the open source option for writing and processing property graphs. And Amazon Neptune is fully compatible with Apache Tinkerpop and the Tinkerpop Gremlin 3.3 release, which is the current one as of August this year. And we provide optimized query execution for traversals that you've written in Gremlin. So here's an example of how you would create a graph using Apache Tinkerpop. This presumes that you've connected to a Neptune instance and you have a remote graph instance, which is here denoted by the variable g. This is a Java example. And you can see on the first line here, we're adding the vertex Bill. You can see we're assigning the label here, user. We're assigning the property Bill. Creating the second vertex, which corresponds to Sarah. And then we create an edge here. And this is the friend relationship. The second graph model that you'll recall is the Rdf Graph Model, or the Resource Description Framework. And Rdf looks a little bit different. Because it has its roots in resource description, the sort of fundamental unit of identification is something that's called an IRI, or an Internationalized Resource Identifier. And it looks just like what you might think of as a URL or a URI. All IRI means this is a fancy way to say that you can accommodate international characters. And you express statements in the graph in this combination of triples. And a triple is made up of a subject, and a predicate, and an object. So if you look at this example across the top, you can see the subject position here is an IRI. It's person. There's a predicate here. In this case, it's RDF type. That has a meaning in the RDF language. It's a user. And they're going to express, in this case, a literal, or like a property, the name Bill. And that combination, that triplet, forms this vertex Bill. Now, the way that you make relationships is you express a triple relationship where the third position, the object position, is not a literal, but is actually another IRI itself. And so if we want to look at making the equivalent friend relationship that we saw in the property graph example, then you can see this is the triplet that would correspond to it. So we start with a subject that is an IRI. We have a predicate here, the friend predicate. And then we have an object which refers to the second vertex that we created. So unlike a certain Starfleet captain with triples, there's no trouble with triples. And so this is a fully example of the same graph looking at RDF. And you can see this corresponds to the Bill vertex. This corresponds to the friend edge. And then the bottom here, you have the Sarah vertex. So let's go through a querying example. We'll go back to looking at relational modeling versus a graph model. But this time we'll look at it from a product perspective. And so this is, again, a very simple relational model. It looks at products and order details and customers. And then on your left-hand side, or I guess on your right-hand side, you'll see the subset of that model represented as a graph. And so if you're familiar with SQL, as I imagine most of you are, this is a very basic query that you would use to answer the question, find me the names of companies that purchase the Echo. And if you look at the query, you'll see that you're joining through. You join up customers, you join order details, you join products, and then finally you make a filter on the name of the product that you're looking for. And so this should look fairly familiar to you. Now if we look at it in Sparkle, Sparkle is the declarative graph query language for the RDF model. You'll see something that's a little bit similar, but rather than having these joins, we're expressing triple patterns, and the triple patterns have shared variables. And that's how we express the same kind of graph pattern. And so in Sparkle, this question mark syntax represents a variable. So again, we're answering the same question. Find me the names of companies that purchased the Echo. The first part, we have a triple pattern where we match the order. The next one is the next triple pattern on order details. Then we go through on the product. And finally, we have the same kinds of filter that we have across the bottom. So that's the example looking at it in Sparkle. In Gremlin, so Gremlin is an imperative traversal language. So the way that you express traversals in Gremlin is by taking them one step at a time. This is how you would answer that same question. Find me the names of the company that purchased the Echo in Gremlin. So we start off with looking for vertices that have a label product that has the name Echo. And then we traverse the edges here for the product, the order details, and the order. And finally, we get the company name. So those are brief examples across a relational model versus graph and into RDF Sparkle and Tinkerpop Gremlin. So let's look at an example application. Looks in using a property graph. So we'll drill down a little bit on the recommendation engine example that we talked about before. This technique is called Triadic Closure. You're looking for triangles or cliques. These are the smallest fully connected subgraphs that you have. And the technique in general is to find cliques that can be completed by adding a single edge. So we have some build issues here. So this is how you would go ahead and make the recommendation. So go back one at a time. So we start off with Terry. We go out one edge hop to Bill. We go out one more, so friends of Bill. And then we complete the recommendation with Terry and Sarah. If you want to look at this in terms of the associated Gremlin traversal, first we find Terry with the label as it, and we use this syntax here as a variable because we're going to want to refer to it again in the future. We follow the friend relationship. We want to express that they're both friends. Then we express where they're not already friends with our starting point, which is where we reuse this variable. And that's essentially how we would implement that very basic recommendation example using Tinkerpop and Gremlin. So let's go through an RDF knowledge graph example. So we talked a little bit about the structure of RDF. And this is another example. In this case, this is using the OpenID data set that's provided by Thomson Reuters. And we're going to go through the example here using Netflix. And if anyone attended the workshop yesterday, you'll see that there's some commonality here. And so just to point out some parts of this graph, here's the URI that represents the identity of the vertex. This is the relationship. This is referring to another entity. One of the things that is powerful about RDF is that it does have a standardized interchange format. And so there's a lot of open data sets that you can leverage. And in this case, there's something called GeoNames. GeoNames is published by the US National Geospatial Agency. And it has a list of place names and identifiers. And so they're pulling in a reference data set here in this example. This is the URI for Netflix. The relationship means where it's incorporated in. And this is that reference data for the country of the United States. So if we look at it again in this example as a collection of triples, we'll see our subject, predicate, and object. That's how that triple expresses that statement. This is an example in RDF of what you would think of as an edge property. And so this case, it's a literal. Literals can be essentially XML data types. And so any of the data types that are valid in XML are valid in RDF literals. And so you can see you have this expressing the name here. And then in this example, you were adding information about the place. And so we have the ISO 3166 country code that we're adding, which we can use for reference information. And one of the benefits of the URI representation that's used in RDF is it's very amenable to being able to link data across different data sets. And so each node and concept in RDF is referred to uniquely. And so you can join different data sets, heterogeneous data sets. And this is a really very common use case that we see customers using RDF for. So how do you query RDF? We showed an example using Sparkle. And so this is how we would query this graph using RDF. You can see we're using a triple pattern here. Again, we're using the variable. And so we want to ask, what's the name of this company? We get back the result. This is Netflix. If we want to take another example, suppose I want to say, what are all the statements about this company? So in this case, we have a triple pattern. Rather than having two of these positions bound, We just have the first one. And so we're going to retrieve all of the different statements about this particular node. And we can see that 2 of them are what we would call literals. And the third one here is an IRI, which would represent a relationship in the graph. And then for one more example here, suppose I want to look for, instead of the name, I want to look for the ID of the organization that's called Netflix, and also pull back its phone number. And here I've created a Sparkle query that has 2 triple patterns in it. They're again joined by the shared variable, the org variable. And so first we match on the organization name, and then we bring in the value of the phone. And so that's sort of a brief introduction to the Tinkerpop and Property Graph Model and RDF and Sparkle. And I'd like to introduce Bruce McGaughey to give you an overview of the enterprise features that Neptune has.
Great. Thank you very much, Brad. Good afternoon. It's great to be here. And we're really excited to launch Neptune and have the opportunity to talk to you all more about it and give you a little more insight into how Neptune works. So Neptune is a fully managed service, makes it very easy to configure things through our console. That's the main way to interact with Neptune today. From there, you can launch new instances, you can monitor the status of instances, you can take snapshots, restore from snapshots. Everything that you want to do to manage Neptune happens via the console. Some of the key benefits of Neptune, first of all, it's multi-AZ, so it has very high availability. And I'll have a little more to say about that in a few detailed slides in just a moment. Next, it supports up to 15 read replicas with a fast failover capability. And we'll look into a little more about how that works in just a moment. We also support encryption at rest, and you can use KMS to manage your keys. We support encryption in transit with TLS. And we support backup and restore. And in fact, Neptune is continuously backing up. It's kind of a unique type of mechanism, which is common to some other engines in Amazon. And so we'll talk more about that as well. And that enables actually some unique features like point-in-time recovery. So first, let's talk about how you deploy Neptune. So Neptune is deployed into a VPC. So you deploy a Neptune cluster endpoint. You configure the VPC security group for the Neptune endpoint. And then you configure another instance, an EC2 instance, with the proper security group settings, which gives you a connection to an internet gateway. And then you query Neptune accordingly from the EC2 instance. And furthermore, I'd like to highlight that the Neptune cluster endpoint, the head node, is allocated into multiple availability zones in the case you have read replicas. So this gives you higher availability for the head nodes as well. So let's take a deeper dive into the Neptune storage engine. So Neptune storage engine is a replication system across 3 availability zones. And in each of the availability zones, there's always 2 copies of the data that are made. And those copies of the data live on storage nodes in 10 gigabyte segments. And each of those segments are then basically correlated across the 6 instance nodes. And there's many, many instance nodes in a particular cluster. And there's some benefits we derive from that around network latencies and being able to spread the network load across a very large cluster. So when Neptune makes reads or writes into its storage layer, you can see that it actually makes 6 network calls into each of the 6 instance nodes. Those storage nodes are actually continuously backing up the data to S3 incrementally. So there's no such thing as kind of checkpointing, which might slow down the storage layer for a period of time. It's happening continuously in the background. And in fact, it's using essentially the same mechanism as when you do a read into the storage engine layer. So it's a very robust mechanism with shared code paths. So if you look at what's happening, there's a storage monitoring capability that's continuously monitoring the health of the native storage engine layer. And whenever any type of problem were to happen with any of those instances, repairs are automatic, and the repairs are seamless. So writes can continue to proceed in the case of failures of up to an entire AZ, or in the case of a single instance, or in the case of a single disk. And the way that happens is the storage nodes have a gossiping capability. They basically correlate with each other to catch up to any of the particular log records that they've missed. So that's what we call a quorum system for the read-write, and that has an additional benefit for performance. It allows the system to essentially hide network latencies. So in the tails of network latencies, we can basically ignore some of those because we require only a quorum of 4 out of 6 in the case we do writes, and a quorum of 3 out of 6 when we do reads. And furthermore, quorum membership changes don't stall writes. So if you need to do an upgrade or swap out some nodes or something, that actually happens seamlessly without any downtime for the database. Storage volumes are not required to be statically allocated. They actually grow automatically up to a maximum volume size of 64 terabytes. So next, let's take a little closer look at what happens with the high availability and the fault tolerance and how the system achieves that. So we all know that a number of things can go wrong in distributed systems. Segments can fail on disks. You can have node failures on machines. Power supplies fail. CPUs burn out. A number of things can go wrong. Entire AZ can go down due to power, network failures, and whatnot. And in all 3 of these cases, we've made optimizations to the storage engine layer so that Neptune can actually withstand any of these types of failures. So for example, on the bottom left, we have a case where 2 instance nodes have gone out simultaneously, which is an extremely rare event, admittedly. In this case, the instance nodes will gossip with each other to patch in any of the missing data. The instance nodes will be replaced, and then the system will catch up and continue processing data. In the case of an entire AZ, we still can achieve a quorum of 4 out of 6 for the writes, so writes can continue. And like we said, only 3 out of 6 is required for a read quorum. So next, let's take a look at the database layer. So Neptune supports up to 15 read replicas. And there's a system that's continuously monitoring the instance health. And if any problems are detected, if a node goes down or if a process goes down, Neptune can actually automatically fail over to one of the replicas and then patch and replace the problem node. Furthermore, the database process is actually split between the head node, which is doing the processing, and the buffer cache. So in the case that your master goes down, or even one of the read replicas, the buffer cache, which takes a lot of network processing to build up, can actually be reused when you reboot the process for the head node. So that allows very fast recovery. You don't have to rewarm the cache in the case of that type of a failure. Next, the replicas are automatically promoted to the primary in the case of a failover. And this can actually be a pretty useful mechanism. So let's say you want to increase the instance size of your master. You simply allocate a larger size master instance. You warm up the cache, and then when you're ready, you can force a failover from the smaller size master to a more capable, larger instance on the replica. And all of this will basically be seamless to the user, and it'll simply show up as maybe a little bit of a slight lag, like a network blip, in terms of the effects on the user. There's also benefits to this approach in terms of the scaling out of customer workloads. And because it's a cluster endpoint, it actually does automatic load balancing for requests. Let's take a little closer look at the failover times. Neptune is able to achieve failover times typically on the order of 30 seconds. So when a failure is detected, it basically takes 15 to 20 seconds for that detection to happen. After that, in parallel, DNS propagation is happening to switch the node over. And at the same time, a recovery process is kicked off to prepare a new head node. And in the case where you have a replica-aware app running, you can actually achieve faster failover times. You can actually bypass the DNS propagation, so you can achieve often less than 30-second failover times. So one of the side benefits, or actually one of, maybe you could argue is the primary benefit of the storage engine mechanism, is that it's continuously doing backups on the fly. So as the instance nodes in the storage engine layer are receiving data from the head nodes, it's writing data into S3, and periodically it's taking segment snapshots, which are points in time where the entire database across the entire storage cluster is consistent. And then furthermore, it's capturing the record logs, and then it can replay them from a particular snapshot in time to any recovery point. And that happens very fast because of the distributed nature of the storage engine. Because every segment is only 10 gigabytes and is spread across a huge cluster, you can imagine that all of the pulling of the data from S3 into all of those storage nodes can happen in parallel and spread the network load across a very large surface area. So the final thing I'd like to talk about is a feature that kind of comes out of the way this storage engine is built, and that is point-in-time restore. So what this is while the database is running, it's constantly doing garbage collection of the segments that are no longer needed. It's doing garbage collection of record logs that are not needed, because the database is caught up. And you can configure Neptune over a period of time, say 24 hours, to not do that garbage collection. Then it actually has all those segments and record logs available. And so you can go back in time then, anytime during that 24-hour period that you've configured, and you can actually have Neptune, in a matter of seconds, restore to a particular point. So let's say you made some terrible mistake. We're all human. It happens. And you delete some really important data. So you can say, go back an hour, and you can check and see, is that data there? If it's not, you can move around, essentially almost like a dial, to choose the point in time that you want to restore to. Then you can even choose windows where you can say, this particular segment of window is invisible, and you can replay past it, and then just continue operations. And this is kind of a natural consequence of the way the engine layer is built. Because it's kind of continuously, incrementally doing its backup, this is actually a feature that kind of falls out of that technology. So that's what I have about the deep dive on technology, and be happy to answer any questions about the portions I talked about or anything that Brad talked about as well.
If you have a question, there are microphones in the aisles. Please step to the microphones to ask your questions.
Hi, quick question on the replication. How do you do it? Do you do it per query or per pages in memory?
I'm sorry, could you repeat the question?
How do you do the replication? Do you do it on a per query basis or per update basis, or do you do it per memory pages?
Oh, okay. The question is, how do we do the, how do we make the data durable, right? Is that happening on a page level? And the answer is that we actually are only writing record logs. So the only record logs are passed across the network rather than entire pages, and that makes it a very efficient system from a networking point of view.
I see. Okay.
Let me take one over on this side.
Do we have the in-memory support of the data?
I'm sorry, could you speak up one more time?
Do we have the in-memory support rather than storing it in the backend?
I'm sorry, one more time, I'm sorry.
Do we have in-memory support of this graph database?
Oh, okay. So the question is, does the graph database support in-memory transactions? Yes, absolutely. So Neptune has a buffer cache where it's buffering as much data as it possibly can on the head node. So obviously, if your entire data set works in memory, then we'll never have to go to disk, except to make things durable, right? But if you're just doing reads or you're doing some type of complex queries or analytics, right, then the entire transaction could remain in memory.
Yeah. This side?
The underlying data store, what is it? Is it a native graph data store, or?
It's a distributed parallel storage system, network-based storage system that Amazon has built, custom for these types of enterprise database applications.
Is it graph or relational, or what's the underlying store?
So the engine itself is purpose-built for graph processing, and then it's using a distributed storage layer underneath of it.
Okay, but the distributed storage layer, what is it? Is it relational or graph or?
It's really neither. It's designed for sort of high throughput, latency hiding for replicating the data across a network of storage devices. So it's really, the storage layer itself is not designed for either relational or graph. The storage engine is designed purposely for graph. On this side.
Hi. Is the 15 replica and 64 terabyte hard limits?
So is the 15 read replicas and the 64 terabytes hard limits?
Yeah.
It is currently. It's not it's a design limitation, but there's no flexibility for you to change it at this point.
Is that going to change ever?
It certainly may evolve in the future. We
Okay.
don't have firm plans to do it.
Thanks.
Sure.
Hi, thank you for producing a highly available graph database. So is there, for RDF, is there language support for string literals?
Yeah, so RDF has full Rdf support for string literals.
Are there any, and is there inference?
We do not have in-database inference currently, so it's really a pure triple store from that perspective. We are very interested in use cases for inferencing and to sort of understand how we might shape the product roadmap in that regards.
And then what happens if a client aborts a query? Like some of the RDF databases have time-limited parameters for query properties that allow you to have an open Sparkle endpoint safely. And of course, a client can just say, oh, this is taking too long and go away, but that leaves the database still performing the calculation.
Right. So we internally have various mechanisms to control limits on query timeouts. Timeouts are something that you, as someone provisioning the service, can use to configure from their configuration group parameters in the console. We also internally have a few other mechanisms that we're looking at figuring out how we can make sure that you can be safe and keep your database working properly.
And what's the maximum number of subjects and triples this has been tested with to date?
So as Bruce said, this sort of storage layer supports up to 64 terabytes. The design target is to support about 100 billion triples, and we've tested it pretty close to that scale.
Okay, thank you.
Is Sparkle Update as well as Sparkle Query available?
Correct. So we support, from Sparkle 1.1, we support Sparkle 1.1 Query, Sparkle 1.1 Update, and then the endpoint itself supports the Sparkle Protocol 1.1.
Perfect, thanks.
How do you feel about multi-tenant datasets where like we have tens of thousands of disjoint graphs that are maybe 10 to the 4 to 10 to the 6 nodes?
So like a use case where you had a very high number of name graphs in a RDF context.
Yeah, like in our case, it's, we have let's say a graph per customer.
Right.
And we, obviously we don't query those at the same time. It's,
Right.
You're always looking at a very small subset of the overall data in the graph.
So the way that Neptune is configured today is it's as a single graph. On the RDF side, we support the name graph, which you can use to create a container concept. On the property graph, we don't have a similar container concept at this point. So our answer for that would be to have multiple very small instances for each of the graphs. But if you have that use case, we'd be interested in hearing about sort of a multi-tenancy graph use case.
Yeah, we'll follow up.
Is the data immutable?
Is the data immutable? No, the data, you can update and change the data.
No, like say for example, the person says, I like pizza, and then tomorrow the person goes and changes to, I like burger. So will I be able to go to the point in time and get what the customer's choice is?
Right, so from a data perspective, you can support those kinds of changes. We don't currently have features that are built in for versioning the graph, across a point in time. Again, that's a use case that we're interested in.
Okay, thank you.
Hi, thank you for the presentation. Sorry, I saw one of the slides, you mentioned some caching. Do you do any caching on the graph, like based on the query or stuff?
Well, the head node is using a buffer pool cache, so there is a very large cache allocated because graph databases work best for exploring relationships when the data set is in memory. So I'd say we're an in-memory optimized graph database, but not exclusively in memory. So the cache technology in Neptune plays a really big role in the performance and the experience that you get out of the product.
So if I do the same query sequentially, I can expect
Yes.
better performance, right?
Absolutely, yes.
Okay.
The first time you do, if the cache is not warm for your working set, obviously it's going to have to fetch from network. And then after that, it'll be in memory, and you will experience much higher throughput.
All right, great. And then can we expect any differences if you use Tinkerpop or Sparkule? Do you have any best practice or for Neptune? Does it work better
really
with
depends
one
on
of them?
application.
Yeah.
So I think you need to choose which stack you want to work on based on which one fits the application best. And both stacks are running on the same storage layer, the same cache technology. An awful lot of the stacks are shared. That being said, they have different properties on those stacks. So you will see some variance in performance.
And one last question, do you have any numbers on the bulk loading? Like, did you test it with, I don't know, compare it to other things like Virtuoso or other?
Sure, so maybe let
Yeah,
Brett handle that.
bulk loading, the design target is 100,000 relationships a second, and we've tested that out to tens of billions of relationships.
Okay, thank you.
Really non-technical question. Why is it called Neptune?
Why is it
I
called
have to
Neptune?
know.
So this was a new fully managed database service. We really felt like Neptune is something special, and so we didn't really want to name it Amazon Graph, for example, which we thought was really didn't speak to the differentiation, and so we just really thought Neptune was something that was interesting. You've got planetary references, you've got Roman mythology. Which one it is up to you. So
up to me to decide.
there you go.
Oh, no, thanks for that.
Hi, thank you so much. We've been waiting for this for a very long time. So I just wanted to ask about two things. First of all, do you have any support for analytics, Olap, long-running queries, and so on? Are those natively supported, or is it more for OLTP use cases?
We initially, the first version is targeted for OLTP use cases. We do have support for Olap processing. There are, the performance is really based on maintaining a ratio of the size of the graph on disk to the size of the memory in the head node. And so there are options that you have to allocate larger nodes to get better analytic performance. But you will be able to get good performance from analytic queries. It's not optimized for full-blown iterative graph analytics.
Right. The other thing is, do you have interoperability with things like Elasticsearch or data sharing? Do I have to maintain replicating my data across these different databases, or do you plan on creating connectors to these?
So today, we don't have interoperability at that level. We do have some customers that have been participating in the pre-preview beta that have done things like Lambda calls to the REST APIs. That being said, as it's emerging, sort of the top new features post-GA are along the lines of graph and search, really developing a story around graph and search, and then things like change detection, something like DynamoDB streams that let you build integrations with other services. So we'd love to hear how you'd like to use it, but that's kind of how we're seeing the feedback we're hearing now from customers.
Great, thank you.
Sure.
Hey, Neptune looks really promising. Thank you. My question is, can we do federated Sparkle queries in Neptune?
So the configuration of Neptune in preview does not allow you to do Sparkle Federation,
Okay.
and that's largely from a security perspective. And so, we're interested, we do see a lot of use cases for Sparkle Federation, but we want to find out a way that you can do it via something like whitelisting or other mechanisms that strikes a balance.
Right, so currently it's more a security limitations to, handle security rather than the engine not having that capability.
Correct.
Okay.
Correct. The engine itself would support this federation.
Thanks.
Do you have any suggestions for migrating data from the relational database to the Neptune right now?
Yeah, so there's a couple different options. You need to sort of see which of the graph models feels most natural to you. We support for a property graph, we support a CSV format that you can use in the bulk load. The CSV format allows you to have nodes and node properties in sets of files and edges and edge properties in files. So from that perspective, you could use something like Glue to sort of develop an ETL job that would take from your relational database and put it into the format that you would load into Neptune. And you could do something similar if you were to choose the RDF representation as well.
Right, thanks.
Sure.
Is there any support for data constraints?
Like Shackle?
A node that meets some criteria cannot be connected to another node that meets some criteria.
So Neptune today doesn't have support for sort of schema concepts or constraints in the graph schema. It is something that we have on our roadmap, and we're interested in sort of understanding the different use cases but it's not something that's there today.
Okay, great, thank you.
So I've seen some documentation online already showing examples of using Neptune over HTTP. Do you also support WebSockets at the moment?
Yeah, so the Gremlin supports both the WebSocket server as well as the REST API, and then on the RDF Sparkle side, it's just the REST endpoint for the Sparkle protocol.
And do you support multiple traversal sources, like per Neptune instance, or would I need to spin up separate Neptune instances to have multiple graphs?
So there's only one graph per Neptune instance, but you could have multiple traversals over that graph with multiple connections to the Gremlin server.
Thank you.
So as far as client libraries go, the client libraries that I saw listed, those are open source, just sort of, they don't really know what's running in the background. Is that accurate?
Yeah, so there's no specific client library for Neptune. The Apache Tinkerpop is an open source project, and there's various different clients that will connect to the Gremlin server, either via WebSockets or the REST API, like the other question was mentioned. And then on the RDF Sparkle side, those are W3C standards, and there's several open source and commercial clients that you can use to connect to the RDF Sparkle endpoints.
Okay, so you guys are running the Gremlin server, that's part of the Neptune product, the server side. So for instance, I spotted a Gremlin client library in Node. Is that something that would work against Neptune
Yes,
as
so
well?
you could take a Gremlin client library in Node, put it on a server within your VPC, configure it to connect to the Gremlin WebSocket, and then use it right away.
Cool, all right, thanks a lot.
Sure.
What is the maximum number of write connections that you can support, and what is your throughput in writes per second?
So maximum of write connections. Bruce, do you have a maximum number of write connections?
We're talking about connections to a particular endpoint, so a very large number, several thousand probably. And then it's a single master system, so only one of the instances will be a write master.
Right. And then from a throughput perspective, as I mentioned, the bulk throughput, which does suspend some of the ACID properties to get a higher throughput rate, is at 100,000 relationships a second. And then under a sustained read-write workload, it's about 20,000.
Okay. Do you plan to support multi-master and multi-master across multi-regions like Dynamo, or is this way beyond?
So we are leveraging sort of the storage layer that's been developed internally at Amazon, and so as there are improvements in that, like multi-master, multi-region, we'll be able to bring them in to offer them as features for Neptune relatively quickly. We don't do that today, but we will be able to do that in the future.
Thank you.
Any size limitation on the nodes themselves?
Any size limitation in terms of the nodes? We do have a blob size limitation in terms of the size of a property, but we don't have any particular limitation in the size of a node from the context of like the number of properties or relationships that it could have.
Or maybe a better question, any hit or any performance problem starting of a certain size of node?
Yeah, so in general, the design of Neptune is such that it should be fairly robust to traverse through supernode type scenarios. Of course, if you do hit a supernode and you want to do a filter on it, and you have to materialize all the property values to do that.
Right.
There's no really getting around the I/O operations, but in general, the design should be relatively robust through traversing through it.
Okay. Next question. Is there integration with language R at this point?
So there are R client libraries that are available for Sparkle, and there are also R client libraries that are available for Gremlin. So there's both options available in open source for you.
Right. Thank you.
When Neptune goes GA, will it be a HIPAA eligible service?
We hope to be HIPAA eligible. Don't quote me on this. I guess I'm on video. When we go GA. And so we're actually starting that process now. So we can't actually get certified until we achieve GA, but at the very least, we hope that it will be HIPAA eligible with a very small delta from being GA.
Is indexing for property-based lookup built-in?
So if you've used an alternative like Titan or Janus Graph, you're probably familiar that to get good traversal performance, you need to explicitly specify indices on properties. And we kind of really see that as asking the customer to do too much and understand the underlying implementation more than they really need to. So Neptune uses internally an indexing strategy that doesn't require you to specify the indices to get good performance. So you should get generally good query performance across Neptune.
So do you have any benchmark against like TitanDB, Janus Graph, and OrientDB?
We don't have anything that we've published currently. We're working on it internally currently, but in general, we're very, very competitive with alternatives.
Okay, thank you.
Yeah, I just want to understand that failure scenario. When the master goes down, you said it takes 30 seconds possibly to recover or to elect a new master, but you're still able to do read queries during that time. Is that correct? Or are you totally no reads or writes during that 30 seconds?
Yeah, I mean, write will stop immediately because of the master. The replicas will continue to read for a period of time, possibly through the whole thing.
Okay, cool. And one more question. Is there any limit on the number of properties or edges that you can attach to the nodes in the graphs? Or
There's no hard limit.
no hard limit? Okay, thanks.
Hi, do you guys, for a directional graph, do you guys offer weighted edges?
Yeah, so in Gremlin, you can have edge weights. Yes. And you can also do it in RDF as well.
And does it have like TTL?
Could you repeat the question, please?
TTL for the edge to expire?
We don't have a TTL feature yet. We have had that come up with a number of customer conversations. So again, it kind of falls in the category, if you have a use case for it, we'd really be interested in it. There's a number of different ways to slice that one.
Okay, thank you.
Just another +1 for the TTL.
Last question. I'm sorry, go ahead.
Just another +1 for the TTL, actually.
Okay, cool, thank you. Great, thank you guys very much. We really appreciate your interest in Neptune.
Thank you.